Hi everybody, welcome to the 3.3 notes. Today we're going to talk about differentiating inverse functions. And so just to recap, what is an inverse function? An inverse function is a function that can reverse into another function. And so for example, say you have two functions and you're told that f of x and g of x are inverses. If the point AB is on the graph of f of x, then the point BA is on the graph of g of x. So essentially, like, the x and the y values are just flip-flopped. And if you look at this graphically, what will be happening is that there's actually a reflection over the line y equals x. So there's a reflection over the line y equals x. And so this is just like a little review, but say we're given the tables of values for f of x. Can we create a table of values for g of x, assuming, this should be added, assuming they're inverses? So if they're inverses, what you do to create a table is I'll write still x, but then I'm going to write g of x. And if they're inverses, all I have to do is just flop the x and the y values. So if in the original function I'm putting in -3 and I'm getting out -26, then in the inverse, if I put in -26, I'm getting out -3. If I'm putting in -2, I'm now getting out -2. And so I'm just flipping all of these values. And so that's what an inverse is. So these two functions are inverses of each other because their points, their x and y values, are just flip-flopped. And so we're just the two function tables that we're actually looking at right now, whether you notice or not, but f of x is x cubed plus 1. So for example, if you cube -2, you get -8. If you add 1, you would get -7. But then g of x, the function is you're taking x, you're taking away 1, and then you're taking the cube root. So example, -7, take away 1 is -8. The cubed root of -8 is -2. And that would work for all of these values. And so sometimes you're going to be asked to confirm that things are inverses. And so one definition of inverses is if you put an inverse function into, like a function into its inverse function, you're always going to get 1 when you simplify. And this is just saying, and it works both ways. So if f of x and g of x are inverses and I put g into f, I'm going to get out an x. But if I put f into g, I'm also going to get out an x. And so that's how you can confirm if things are inverses or not. So we'll go ahead and confirm this. I know I told you they're inverses, but let's confirm that this works. So starting off, I'm going to find f of g of x, and I'm just confirming that this equals x. And so what I'm going to do here is I'm going to do blank cubed plus 1, and then I'm replacing my input x with 3x minus 1. When I go to evaluate these, the cubed root and then cubing, they're inverses of each other, so these cancel each other out, and you get x minus 1 plus 1, and you get that simplifying to x. So I've confirmed that it's an inverse that direction. If you're being asked to confirm it, you have to do it in both directions, though. So now I'm going to do g f of x. No derivatives happening so far yet. We're just talking about inverses. So I'm plugging in x cubed plus 1 in for x in the g of x function. So I'm doing 3 square root x cubed plus 1 minus 1. And this equals the cubed root of x cubed plus 1 minus 1, which equals the cubed root of x cubed. And again, the cubed root and then a cube are inverses of each other. So I'm getting x. And so I have just confirmed that these are inverses of each other because they equal 1. And so this rule is going to be really important in a second, because notice this inverse rule right here, those are composition functions. You're putting one function into the other function. And so in a second, we're going to use the chain rule to differentiate. We're not going to do it just yet. The chain rule is actually going to help us find a shortcut. We're going to do the long way first, and then we'll start to go into the shortcut versions. And so this first function says, let f of x equal x cubed. This is crazy notation and it looks terrible, but this is asking what is the inverse. This means inverse. This means what is the inverse of f's derivative, right? This is the derivative symbol at 8. So we need to find the inverse's derivative at 8. So before we even start, let's just write out, like, what do these function tables look like? We're just going to do this over the side just to, like, continue to help us conceptualize what an inverse is. So if the original function is f of x, and that's x cubed, let's just do some positive values right now. So if I plug in 0 into the f of x equation, 0 cubed is 1. If I plug in 1, 1 cubed is 1, 2 cubed is 8, and then 3 cubed is 27. And so hopefully that should be just like enough to get us started. Then the inverse of that table is just going to be all of those points flip-flopped. So if I put in 1, I'll get out 0. If I put in 1, I'll get out, oh, sorry, I don't know why I said this was 1 either. 0 cubed is 0. Sorry about that. So I put in 0, I'll get out a 0. If I put in a 1, I'll get out a 1. If I put in an 8, I should get out a 2. And then if I put in a 27, I should get out a 3. Okay? So notice that this point right here, we're being asked to find the inverse derivative at 8. And so we do know, this will help us maybe later, but we do know that the inverse's output at 8 is 2, but we're being asked to find the derivative. So that doesn't really help us right now. But if I'm going to do this, the very first thing I'm going to do to actually answer this question is if I want to find the inverse's derivative, I actually need to have the inverse. And so this is a little bit of a recap too, but f of x equals x cubed, and you can find an inverse if you are given an equation. So what you do is you first take it out of function notation. So I'm going to make this y equals x cubed. F of x and y are both ways to represent outputs. But sometimes we use some over the other. And then what you'll do is you'll flip your x and your y value. So you'll do x equals y cubed. And if you think about that, that makes sense. Like an inverse, it's just the x and the y are flipped. So you'll flip them, and then you'll go ahead and solve for y. And so I'm now going to solve for y. So I'm going to say flip, and now I'm solving. So to get y by itself, I just need to cube root both sides. And then this will leave me with the cubed root of x equals the cube, like we already talked about this, but those are inverses of each other, so I'll get y. And so I'm told right now that the inverse equation is the cubed root of 8, which makes sense because the cubed root of 8 is 2. Like that fits the table here too. Now I'm going to find that derivative. So my next part is I'm going to find the derivative of this. So much ugly notation. I'm going to rewrite this as x to the 1/3 down here because that will help me take the derivative. I'm going to keep it in exponential form. And so I will drop down the 1/3 and I'll get x to the negative 2/3. And because I'm asked to evaluate this at 8, I'm going to go ahead and simplify this to make my evaluation step easier. So this is going to be equivalent to this. So this is the derivative of the inverse, but this is the derivative of the inverse simplified to help me find the derivative of the inverse at 8 easier. So now I'm actually going to plug in 8, and that gives me 1/3 cubed root of 8 squared, which is going to simplify to 1/3 cubed root of 64. The cubed root of 64 is 4, and so I'm going to get 1/12. And that is the answer, and we are done with that. We're going to do some fun things over the side, but that answers the question. That is the inverse of the derivative. That is the derivative's inverse at 8. But I want us to notice some patterns because that was obviously a lot of work, and so the question is, are there shortcuts? And a lot of times there are shortcuts. So to notice the pattern over here, I'm going to realize that I highlighted over here the point 8,2. That point is the point on the inverse, but that coincides with the point 2,8 on the original function, right? Those are like inverses of each other. They go together. And so watch what happens when I take, I'm going to take the, so I guess I'll write out the original function, but watch what's going to happen here. I'm going to take my original function, and this is not helping me answer the question. I'm just trying to help you notice some patterns, but the original function is x cubed. The derivative of that is 3x squared. And then watch when I plug in the input value 2. I'm not plugging in 8 because I have to plug in x's, but I do 3 times 2 squared, and that gives me 3 times 4, and that equals 12, which is very similar to this, except it's the inverse. The inverse of 12 is 1/12, okay? So hold on to that. We're going to do another problem. So this next problem, same idea. We are going to just do this by hand. We're going to first we're being asked to find the derivative of the inverse at e to the 2 power. So I'm going to start by finding, if I want to do anything, I need to start by finding the inverse. So I'm going to change this to y equals e to the 3x, and then I'm flipping my x and y. Flipping my x and y, and then I'm solving for y. This is the reason we're going to learn shortcuts, is because you might not remember how to solve this function right here. So what you do to undo a function where the base is an e is the inverse of that is the natural log. So I'm going to take the natural log of both sides. And then there is a rule when you're working with logs and natural logs that you can move the exponent on your piece that you're plugging in out front. So I'm going to do times 3y, the natural log of e. And then I already said that the natural log was the inverse of e. And so that means, and you can plug this in your calculator, but the natural log of e equals 1. So now I'll have the natural log of x equals 3y, and all I have to do to simplify is divide 3 on both sides, and I'll get the natural log of x over 3 equals y. And I'm going to go ahead and write that as 1/3 the natural log of x, because that will help me with the derivative a little bit. So this part right here is the inverse part. So now let's take the derivative of the inverse. That's just going to be 1/3 times the derivative of the natural log is 1 over x. So I'm going to get 1 over 3x. And then if I want to plug in e to the 2 power, which I have to do, I'm going to get 1 over 3 to the e squared power. And that is the answer. So we are done, but that was a lot of work, and you had to know some background information. So to make a connection between the derivative and the original function, so I'm going to make a little mini table over here. So we just plugged in e to the 2nd power into this function. And so we plugged in e to the 2nd power into the inverse function. We put it in as an input. That means on the original function, it would be an output. The question is, what is the x value that goes with that output? But we can just solve for that, right? We'll just do, and also I'm sorry that this should say g right here. That's my bad. So we can solve for that x, and you'll see why we're doing this in a second. So if I want to solve for x and I know the output is e squared, I'll just do e to the 3x power equals e squared. And there's a rule that says if the bases are the same, their exponents are equivalent to each other. So I'm going to do 3x equals 2, and I'm going to divide 3 on both sides. I'm going to get x equals 2/3. So the input that goes with the output, e to the 2nd power, is 2/3, which means if I'm plugging in 2/3 and then I'm getting out e squared on the original function, then in its inverse, if I plug in e squared, I'm getting out 2/3. So these 2 points coincide with each other because they're just the inverse of each other. And now watch what happens when I find the derivative of the original function. So I'm just going to go, so the original function, just a reminder, is e to the 3x power, and using the chain rule, I'll get 3e to the 3x power, and then if I were to plug in that input value, 2/3, I would get 3e times 3 to the 2/3 power, which is equivalent to, those 3 cancels out, that's equivalent to 3e squared. And notice that those are the same, but they're inverses of each other. And so here is where the trick is coming, so that you don't have to find the inverse, because you really don't actually always need to find the inverse. So this is how we're going to give you that key idea, derivative of inverse key idea. So if given f of x and g of x are inverse, let's determine how we could find g prime of x. If g is the inverse in this situation, so if we want to find the derivative of the inverse in terms of f prime of x, okay? So this says differentiate this function implicitly. So earlier we were told that if a function is an inverse of another function, that when you plug them into each other, they always simplify to x. And look, that's a composite function. So watch what happens when, I know that this rule is true, right? But I want to figure out how I can more easily find the derivative of inverse functions. And so I need to take the derivative of this function. So if I take the derivative of both sides of this function with respect to x, because that's my independent variable here, I'm going to get, well, this is just a composite function, so I'm really just going to get the chain rule out here. I'm going to get f prime of g of x times g prime of x, and that's going to equal 1, because the derivative of x is 1. And then the original problem said determine g prime of x in terms of f of x. So I'm going to solve for this, and that's going to give me g prime of x equals 1 f prime of g of x. So we have done a ton of setup, but what you need to know is that if you are ever asked to find the inverse of a function, which is what this is saying, if you want to find the derivative of the inverse of a function, you basically do 1 divided by the original function with the inverse plugged in. And so that is the key idea of today. And now, instead of having to do all this work where we actually have to find the inverse and all of those things, I can just use this key idea. So we're going to continue on and doing a couple examples. I know that this is a lot and it's kind of confusing, but you'll get the hang of it eventually. So this function says, let f be a differentiable function such that f of 5 equals 20, f of 7 equals 5, f prime of 5 equals negative 4, and f prime of 7 equals negative 5 halves. The function g is differentiable, and g of x equals f prime of x. G of x equals the inverse of x. So this just means like this is f's inverse. So what is the value of g prime of 5? So what we're being asked to find is the value of g prime of 5. So if I use the rule that I was just given, I'm going to find g prime of 5 by doing 1 divided by f prime of g of 5. So I need a couple pieces of information here. Real quick, I don't have any equations, right? So I need to be able to figure out all these values without having any equations. But notice it's telling me to find g of 5. And nowhere here am I told what g of 5 is. But I am given a couple random values for f of x, right? I'm being told that if I plug in 5, I'm going to get out of 20. If I plug in 7, I'm going to get out of 5. And remember that that would mean then, since this is the inverse, these points are also found on the inverse function, but they're flipped. So if I plug in 20, I'm getting out of 5. And plugging in 5, I'm getting out of 7. So that means that g of 5 is 7. And then I'm asked to find, I need to find f prime of 7, and that is information that I'm given. It equals negative 5 halves, and if I simplify that, I get negative 2/5. So the inverse is derivative at 5 is negative 2/5. And obviously there's no other way to do this because we didn't have any equations, but this is often problems you're given, and it really is like so much quicker than everything we just did. A couple more problems. Now this is an equation, but I'm still going to show you how can we use this as a shortcut. So it says the function h is given by h of x equals x to the 5th power plus 3x minus 2, and h of 1 equals 2. If h to the negative 1 power is the inverse of h, what is the value of the derivative of the inverse at 2? So many words, but I'm going to go ahead and use this rule, which tells me that so in this case, we're not defining the inverse by anything, but we're just calling it like it's inverse notation. But I'm going to write the inverse of h, which is 1 over h of the inverse. So sorry, this should say the derivative. So that is like this same rule. It's just like a little different because we were told like, oh, g is the inverse of f. Now we're calling the inverse of h, like we're just using the inverse notation. So inverse notation, derivative, 1 divided by the original function with the inverse plugged in. And we want to find the inverse at 2. Sorry. This is a prime. 1 over h inverse 2. So the first thing that we need to do this problem is we need to figure out what the inverse's value is at 2. But remember, this is the original. So the original function has a point at 1, 2, which means the inverse then has a point at 2, 1. So I know that this is equivalent to 1 over h to the 1 power. Okay, so 1 over h, and sorry, this should have a derivative symbol right there. Derivative symbol. And so now all I have to do to figure this out is I just need to plug in 1 into the derivative. The derivative of h of x is 5x to the 4th power plus 3. And so all I need to do is do 1 over 5 times 1 to the 4th power plus 3. And that gives me 1/8. And that is the answer. And that is so much quicker. Like if you were to ask to find the inverse of this, like it would just, I don't even know if it's really possible. It would take you so much time. And so that is why we have this rule right here. So we'll do two more problems. And then, wait, this is the same problem twice. So we got lucky. We only have one more problem. So here's our last one. It says g and h are inverse functions. We're being asked in the end of the day to find h prime of 3. We're being given some values for g of x and for h of x, and then we're given only the derivative of g of x. So my notation for this is h prime of x is going to be equivalent to 1 over its inverse. So h is inverse is g. But since it's prime, this is going to be prime, and then all over h of x. And in this situation, we're trying to find the 3. So we're going to get 1 over g prime of h of 3. And now I'm going to fill in some values. So h of 3, oh, we actually are given h of 3 this time, so that is really nice. So I'm going to do 1 over g prime h of 3 is 4. And then g prime of 4 is 1/2. So I'm getting 1 over 1/2, and that equals 2. And so that one was a little easier because we were given all the exact information. So that is this whole video. I know it was long. Try your best, and let me know if you have any questions.